inverse trigonometric functions, along with logarithmic functions, are probably the most challenging, the most problematic of all core functions that are studied in pre-calculus and calculus. There are several reasons. I think the main ones are they are inverse functions first and foremost, which makes them difficult to understand because inverses are inherently difficult. And for inverse trig functions, especially these ones, I mean, you've got to understand your core trigonometric functions very well. So if you don't really understand sine, cos, and tangent, there's no hope really of understanding the inverse functions, along with the fact that definitions are very subtle for the actual inverses, as we're going to see. So the aim is the following. So we want to define inverse functions for sine, cos, and tan. So find inverse functions for sine, cosine, and tangent. We're not going to do the other ones, things like cosecant, secant, for several reasons. First of all, they're not so important, and secondly, there isn't actually a completely uniform definition for them. Right? As we're going to see, there are going to be certain arbitrary choices we're going to make in a moment, and the arbitrary choices are not completely agreed on for the other ones. Different people have slightly different conventions, but we're going to completely ignore it. We're only going to think about sine, cosine, and tangent. So there's a massive problem here. A huge issue. I mean, for an inverse to exist, you've got to be one-to-one, and sine, cosine, and tangent are very not one-to-one. And if they're not one-to-one, they don't admit inverses. So that's immediately a huge problem, and we can visually see this, right? If we plot the graphs, so I'm cheating, I'm bringing these in, it takes so long to draw them. But if I have my graphs of them, it's hugely obvious they're not one-to-one because of their periodicity. So if I was to draw any horizontal line, either I hit it 0, or if I do hit it, I hit it multiple times. And all it requires is one line to mess things up, remember. And that's exactly what's going to happen with all of them. So this line down here for sine, no good at all. I hit infinitely many times, and it's got to be exactly one or not at all. Same thing here. So we've seen this when dealing with each of these graphs. We've seen it from several perspectives. We've thought about it from the perspective of the unit circle definition, which is, of course, the most fundamental way to think about this. But we can see from the graphs immediately all of them fail what they need to pass to have an inverse. So all fail the horizontal line test. No good, right? If they all fail the horizontal line test, that means they don't have inverse functions. So there we go, we can stop the lecture, right? Over, no inverse functions. But we are going to attempt to rectify the situation. So sine, cosine, and tangent do not have true inverse functions. So when I say true, I mean thinking about them on their whole domain, that kind of business. So true inverse functions. A little bit like x squared doesn't have a true inverse function. Square root is kind of only a partial inverse once I restrict the domain of x squared. So they do not have true inverse function. Right. So how do we deal with x squared? Well, as I said, for x squared, you're not one-to-one. For example, minus 1 squared is equal to 1 squared is equal to 1. But if we restricted the domain, if we essentially threw away all the negative inputs, then you've got half a parabola. That suddenly satisfies the horizontal line test. It's one-to-one, so it's got an inverse. And the inverse is our usual square root function, where the square root, by definition, is the positive of the two square roots. So that's what we want to do here. We want to basically take these graphs and restrict them so that they become one-to-one. But we do want to do it in a way that preserves the range. We don't want to lose the range. So here's the basic fix. So this is kind of a workaround. So partial fix. Because it doesn't truly solve the problem, because they are truly not one-to-one. But we're going to restrict the domains such that, so I'm going to try and do this for all of them. The first thing I want to happen is, as I said, I want to preserve the range. I want the range to be the same. So the range is preserved, so we don't lose any possible outputs. And 2, we want them to be one-to-one. Of course, right? We need one-to-one. Absolutely crucial. Right. So let's just go back up the top a second. So what are we trying to do? We basically want to chop up these graphs in a way that keeps the range the same. So for example, for sine and cos, it's got to still be the closed interval from -1 to 1. And of course, for tan, it's got to be all real numbers. But we've got to stop this nasty stuff about these horizontal lines hitting infinitely many positions. Now, visibly, there's loads of ways to do this. For example, for tangent, I could restrict everything. So it's just going to be only this, for example. That would be an option. Right? If I threw everything else away apart from that, it would be 1-to-1, it would have the same range. But I could equally well do it over here. Or over here, or any of these guys. Same thing for sine and cos, right? I could, for example, for sine, choose... What could I choose for sine? I could choose this. Only that. Throw away everything else. So if I do that, the range stays the same, and I lose this issue of the horizontal line test failing. But there's loads of other options. I could choose this equally. Couldn't I? Same thing for cos, right? You could choose this. Or you could choose this. There's just tons of options. So this means we've got some choice here. And there's no kind of natural overall way to do this. But there is a convention that we have decided on as mathematicians and scientists. And the following is the convention. So here are restriction conventions. So this is one of the things that makes this difficult. So for cosine, so let me kind of go off a moment. So for cosine, let me kind of grab this graph. So here's what I'm going to do. So let's get rid of this horizontal business. So I need to restrict it. So the convention we make is we're going to restrict it between 0 and pi. So that means we're going to restrict the graph to be basically this piece of it. So again, there's no completely canonical, no natural reason for that. It's just a decision that we've made. So if I do this, what's going to happen? I'm going to be left with this. Now that preserves the range, of course. Still between, this isn't the best picture ever, but it's still between -1 and 1. And it's 1-to-1 now. All right, so if I draw any horizontal line, it either hits it once or not at all, which is exactly what I'm looking for. So this is the restriction that cosine is restricted to the open interval, the closed interval, because it's fine to contain the endpoints. You need those for -1 and 1, 0 and pi. Right, that's the convention we make. What about sine? So for sine, let's go upstairs and grab this again. So again, we've got loads of options, don't we? Loads of options. And there's no completely natural one, honestly. But the one we choose is this guy. So let me just show you the one that we choose. We're going to choose this. That piece there. There are kind of various reasons these are good choices which kind of turn up later on, but for the moment it's pretty arbitrary. Nice. So this is what we're going to choose, and let's just make sure things are labelled properly. This point here, oh my goodness, this point here would be minus pi over 2. So I can see what I'm doing here. I'm restricting to minus pi over 2 to pi over 2. So sine is restricted to minus pi over 2, inclusive, because this is where you have minus 1, 1, to pi over 2. Neat. What about tangent? Well, this one I think is a bit more obvious than the others, or it's a more obvious convention. Remember, it's an arbitrary choice, right? There's no kind of definitive reason for these particularly. Let me write this like this. So in this case, let's get rid of this problematic stuff. So we need one of these kind of elongated S's, don't we? So it makes a lot of sense just to choose the central one. So we're going to get rid of everything else. Let's try and be as neat as possible. Right, that seems like a sensible choice. So clearly now we're going to be restricted to, so tangent to, okay, so now you can't involve the endpoints. The endpoints would be minus pi over 2 and pi over 2. Those both correspond to an undefined tangent because you'd be dividing through by 0 with the cosine. So it's an open interval, pi over 2, minus pi over 2 to pi over 2. So the first two are closed, second one open. Wrong. So this is closed, sorry. And this guy is open. So I now have functions which are defined. They're obviously extremely close related to sine and cos. They are different though, because they have slightly different domains, or very different domains, restricted domains, but they're one-to-one. That means they've got inverses. So I'm going to define the inverse to cos, the inverse to sine, and the inverse to tan to be the inverses of these restrictions. Okay, so they're not going to be true inverses. They're going to be partial inverses in a sense. Just like the inverse to x squared doesn't truly exist, but if I restrict x squared to positive numbers, then it would be the positive square root function. So definition. Definition. So here's more little details that can cause all sorts of problems. I don't want to define cosine, sine, and tangent with the notation I'm used to for inverses. I don't want to write cosine to the -1, tan to the -1, and sine to the -1, because those are very easy to confuse with the reciprocal notation. So instead, we write, for historical reasons, and there are mathematical reasons for it, we write, instead of, for example, the inverse cosine to the -1, we write arc cosine. So arc cosine is going to be our inverse function, our inverse of the function cosine restricted, so I'll say arc cosine, is equal to the inverse of cosine restricted to this interval. Because we can't truly take an inverse because cosine is not one-to-one, but if I restrict it to 0 to pi, then it is one-to-one, so that, what am I doing? This is arc cosine, perfect. And again, a reason I'm not doing this is just because of silly notation, but some textbooks do this, some don't. I'm very strict about this just because it causes so many notational problems. This is sometimes written as cos to the minus 1. Makes sense, but be very careful. This is not equal to 1 over cos, as you might think. But we've talked about this before. If I have a function f, cos to the minus, or f to the minus 1 is the inverse function. The problem is, and the reason I'm avoiding this is because remember when I wrote things like cos squared theta? Well, that did mean cos of theta all squared. So it really doesn't gel well with this notation at all. So that's the reason I'm avoiding it. So this massively isn't 1 over cos, right? Absolutely not, right? Arc cosine is not 1 over cosine. That's a massive mistake I see a lot. Just like the inverse of a function is not 1 over the function. So if that's something you've thought before, it's time to really take a deep breath and go through this carefully, because that's a massive error. Arc cosine is absolutely not equal to 1 over cosine. No, no, no. Right? And the reason you're probably confused about that is because of this bad notation, right? Which makes you think it's 1 over. Arc sine. Exactly what you think. This is the inverse of the sine function. But again, you've got to be restricted, don't you? In order to be 1 to 1 and have an inverse. So restricted to, well, now it's the closed interval, just as I wrote a moment ago. So I'll scroll up in a second. It's minus pi over 2 to pi over 2, closed interval, to keep the range minus 1 to 1. So that's exactly this middle case. Finally, arctangent. Not to be confused with 1 over tangent, absolutely not. It's a long way from that. Arctangent is equal to the inverse of the tangent function restricted to, now this one is a bit more delicate, remember, it is the open interval, because we can't take tangent of minus pi over 2 or pi over 2. So this is the definition of the inverse trigonometric functions. Right? It's not 1 over tan or 1 over cos or 1 over tan or 1 over sine. It's the inverse function to cosine, sine, and tan restricted. So these are our inverse trigonometric functions. And I said a moment ago, at the beginning, we're not going to look at things like inverse or arc sec or arc cosecant or arc cotangent. A reason for that is you would need to do the same thing. You would need to restrict the domain in some way of secant, cosecant, or cotangent. And there's no completely agreed upon convention for that. So those functions are a little bit ambiguous when it comes down to it. But these ones are not. These conventions are completely universal. Everyone uses them. This is the definition of these inverse trigonometric functions. So next time we're going to look at the properties of these really carefully.